I'm honored to attend this online conference. Firstly, I sincerely wish this conference can be successful. My name is Zeyu, and I come from Xi'an Jiaotong University. Today, the title of my presentation is Performance Analysis of Radar Communication Shared Signal based on OFDM. Next, I will make this report from 5 parts, which are respectively background, signal model, ambiguity function, simulation and analysis, and a conclusion. There's a lot to say when it comes to background, and I will make 3 brief points. With the explosive growth of wireless devices, spectrum resources are strained in recent years from the perspective of the working frequency band, signal waveform, system structure, and information processing. The difference between communication and radar gradually decreases. With the new emerging scenarios, no matter in military or in civilian, people realize integrated radar and communication is a good way to solve the problems above. The one of core issues of dual functional radar system communication system, as shown in Figure 1, is the integrated waveform design. Considering the advantages of OFDM signal in both in communication and radar, such as good anti-multipass performance and high resolution, it's an appropriate choice. Next is about signal model. The Figure 2 shows the traditional OFDM radar transmitted signal. We can find it only sends one OFDM symbol in each pulse repetition interval, and it usually doesn't consider the communication information, so it doesn't contain the cycling prefix. If you use this signal as a radar communication shared signal, it has low communication rate, and the synchronization is also difficult. So we take the OFDM radar communication shared signal as shown in Figure 3. And it sends more OFDM symbols in radar pulse repetition interval. Meanwhile, we add cycling prefix compared with traditional OFDM signal in communication. The follow is the baseband expression of the shared signal, where NS is the number of OFDM symbol, and NC is the number of subcarriers. ANM represents the communication date modulated on the nth subcarrier of M's OFDM symbol. Fn is the frequency of nth subcarrier. Delta F is the subcarrier interval. Rect is the rectangular window function, and the TCM is the full OFDM symbol time. Then is turned to ambiguity function. As an important tool for radar waveform design and analysis, ambiguity function can describe the characteristics of waveform and corresponding matched filter. By analyzing the ambiguity function of radar transmitted signal, the resolution, measurement accuracy, and the ambiguity of radar system can be obtained. We adopt the ambiguity function expression defined from output of the matched filter. As we can see in red and blue box, there are two important parameters in expression, where tau is the relative time delay and Fd is the Doppler shift. Then we derive the closed form expression of ambiguity function. Based on the value range of delay tau, we discuss three cases. Case 2 and case 3 are correspond to figure 4 and figure 5 respectively. Now let's skip the complicated integration. When the Doppler shift is equal to 0, we can get the range ambiguity function, which is also the zero Doppler cut in simulation. The range ambiguity function is the complex correlation function of the signal, and also the output response of signal through its match filter. When the relative delay tau is equal to 0, we can get velocity ambiguity function, which is also zero delay cut in simulation. After we derivation, the velocity ambiguity function is in the shape of the sinc function, and its mean lobe wise is inversely proportional to the pulse wise. On the right side, we also give the evaluation indicators, such as peak side lobes ratio (PSLR), integrated side lobes ratio (ISLR), and mean lobe wise MLW. PSLR is defined as the ratio of the highest side lobe peak (PS) to the mean lobe peak (PM). ISLR is defined as the ratio of side lobe energy (ES) to mean lobe energy (EM), and the mean lobe wise is used to measure the range resolution and the velocity resolution. By the way, simulating the closed form expression of ambiguity function is difficult, so we adopt a fast algorithm. The main idea comes from the time domain convolution theory. That is, the convolution of two signals in time domain is equal to their product of the Fourier transform of two signals in frequency domain. The fast algorithm process is shown in figure 6, which corresponds to the formula in the red box. Notice that we used oversampling in order to make the simulation curve show more details. And now we talk about the simulation and analysis. On the left side, we give the setup of simulation, such as QPSK modulation. The number of OFDM symbol AS is 10. The number of subcarrier NC is 16. The basic OFDM symbol duration T is 1 microsecond. The subcarrier interval delta F is 1 megahertz. The guide interval Tg is quarter of the basic OFDM symbol duration. The full OFDM symbol time TCM is 1.25 microsecond, and the oversampling factor is 16. On the right side, the figure 7 shows the simulation result. The figure 7a is is the ambiguity function, and B is a zero double cut. C is a zero delay cut, as can be seen in Figure 7a. The ambiguity function of the OFDM radar communication shared signal has a sum back shape with single central peak. As can be seen in Figure 7b and C. A narrow central peak implies high range and velocity and Doppler resolution, so it has a high accuracy of range and speed measurement. On the other hand, there are some fluctuations in the saddle loop region. It may affect the detection of the target. Then, we fix the number of OFDM symbols NS, change the number of subcarriers NC to explore the influence of the NC on ambiguity function. As can be seen in Figure 8 and the data in Table 1, especially the data in red box, we can find the main lobe-wise MLW of zero delay cut is approximately inversely proportional to the NC. Namely, the main lobe-wise reduces the double when the NC is doubled, and the ISR integrated saddle lobe ratio ISLR of zero delay cut decreases gradually with the increment of NC. Other parameters don't change significantly with the increment of NC. So, because of the reduction of MLW in zero Doppler cut, the increment of NC improves the inherent range resolution of shared signal, which is approximately inversely proportional to bandwidth, but has little effect on the saddle lobe characteristics of zero Doppler cut, which is also range on ambiguity function. Meanwhile, because of the reduction, decrement of ISLR, the saddle lobe characteristics of zero delay cut is improved to some extent, which is correspond with velocity ambiguity function. Next, in the same way, we fix the number of subcarriers NC and change the number of OFDM symbols NS to explore the influence of NS on ambiguity function. The conclusion is symmetrical with the above. Because of the reduction of main-lobe-wise MLW in zero delay cut, the increment of NS improves the inherent velocity resolution of the shared signal, which is approximately inversely proportional to the pulse-wise, but has little effect on the saddle lobe characteristics of the zero delay cut. Meanwhile, because of the decrement of ISLR, the saddle lobe characteristics of zero Doppler cut is improved to some extent, which is correspond with range ambiguity function. Then let's find the influence of the cycling prefix. When the relative delay is equal to basic OFDM symbol duration, the integral of the ambiguity function is shown in Figure 10. And due to the cycling prefix, the correlation between the two signals will be exactly equal at the second prefix part of each OFDM symbol, which causes a symmetric pseudo-peak, and it will be introduced into the range ambiguity function. As shown in figure 11a, the zero Doppler cut shows a symmetric pseudo-peak at the point where the delay tau is plus or minus 0.8. In this case, zero padding can be chosen to replace second prefix to eliminate the appearance of false peak, as shown in figure 11b, obviously. Oh, finally, I'm just giving the conclusion before, so let's skip this part. As for future work, we will discuss the radar target detection performance and the communication performance of integrated signals. That's all about our work. Thanks for your listening.